Hello, Shapleski here, related rates, day 1. I started by blowing up a balloon. Please Google blowing up a balloon video and watch it blow up. All right, now this is what we did just kind of the other day, and I want to show you the difference between differentials and related rates. They're similar, but they are different. Okay, so you don't have to write this down because this is a review problem. I think this is the exact same problem I did yesterday, and you did on your homework, so you did it twice. Consider the sphere of a radius 10. Okay, let's just say the balloon started by being blown up. The radius then changes by 0.1. That would be a dr, change in radius, a very small amount. How much does the volume change? dV. This was your homework. This is a review. You need to start with the volume of the sphere formula. Hey, Shapleski, do you have to memorize that for me? I'll tell you in a second. So then you take the derivative of v, you get dv. You bring the 3 over, they cancel, you get the 4, and then you lower the power, and you need to tack on a dr at the end, because you're taking the derivative of radius. And then you plug in all your stuff. Because this is the change in radius, you put the 0.1 right there. The question is asking you for dv, you get this. I do want you to remember that this is an approximate change in the volume. Okay, dv. That's approximate. So what does R stand for? What does V stand for? What is dr? And dv. Okay, that's important to understand because now I'm about to hand out, which will be available on Facebook and on the staff share, student share, a related rates and optimization. I put them on both. A help sheet for you with formulas. Made this up this year. I did it over the last couple weeks trying to remember all the formulas. I'm sure I missed a few because there's lots, but we'll add to it and I'll even make this better next year. I am now going to think about, as I hand out this related rate sheet, this problem. So take one of these and look on the related rates side. As you do your homework tonight, your homework is a combination of a couple beginning related rates problems and it's a couple optimization problems. The optimization problems I'm having you review because you're going to have a quiz on optimization on Friday. Okay, it was meant to be tomorrow, but I am going to move it back one day so we can do a little review and get that review and process that review. Need another one? Okay. For this related rates problem, we're going to be looking on the front, and Trey or somebody earlier asked, do you have to memorize these formulas? Look at the bottom of the sheet. You might want to put marks by the formulas you have to know. They expect you to know what's called the simple formulas. They expect you to know the area of a circle formula, pi r squared. And they expect you to know circumference, 2 pi r, or pi times d. They expect you to know a rectangle, length times width. You're going to do thousands of rectangles in a few days, and you'll understand that when we get to that section with chapter 6. Surface area of a sphere, surface area of a cylinder, prism, not really. They don't expect you to know those. They'll probably give them to you. Box might be an exception because you can do length times width of each side and add all 6 sides. That might be the only exception. Volume formulas there. Honestly, you should know the cylinder formula, but I believe they give that to you too. But all of those volume formulas they give you. You have to know the last 3 though. Pythagorean theorem, all your SOHCAHTOA stuff from trig, and similar triangles we'll get to later. Those are challenging. But you'll see similar triangles. So let's look at this problem here that I'm about to give you. Now suppose that the radius is changing at an instantaneous rate. Now this is different. This isn't a dr. If I change the radius 0.1, that's a dr. Because this is centimeters per second, it's not just our friend dr, it's dr dt. It's the change in radius, let me write this, dr dt. And it comes from your units. It says radius changing, so you know you use the delta or the d. And it says centimeters on top, that was a radius change. And it says time on the bottom per second, that's a time change. Everything in related rates is with respect to time, almost everything. Possible if the sphere is a soap bubble or a balloon. So here's our picture of our soap bubble. So first of all, you're going to need to start with a formula. So I'm going to start with a volume because I'm going to do a similar thing to what we did here. On this last one, radius of a sphere, same problem. The only difference is this dr here was not a dr dt, just a dr. Everything from this point forward is dr dt because it's changing at a rate. So the radius in this case is getting consistently changed, okay, at this instant. So you start with the volume formula because the previous question had about volume. Okay, so now how do I get these dRs and dVs? You take the derivative. Go ahead and take the derivative. Everything's about derivatives. Which is the same thing I did earlier. And which ends up to be this. Now, a couple comments here. Comment number one. It's really a no-brainer to go from V to dV. Don't forget here, though, that if you're talking about this graph, you're not changing the volume of the soap bubble or whatever it is. You're not changing the volume with respect to the radius. You're changing the volume or the radius over time. Since t is your variable, anytime you see a t in the problem, you don't need a t prime. Remember when we did derivatives of stuff like this? 2y plus 2x equals 7. We took the derivative of 2x and we got 2, right? We took the derivative of 2y. What do we get? 2y prime. Why do we need a y prime? Because the variable is x and y is not an x. Y is a function of x. So even though my volume is a function of r, the thing that's changing over here is time. So time is always my independent variable, the thing that gets changing over time. It's always for these kind of problems. So if you ever have a t in these problems, and you almost never do, you don't need a dt, because that's 1. You could if you wanted to. But because r is not t, you need a dr dt. Just memorize that if you don't understand kind of what I'm saying. It's as simple as can be. And then you start plugging in your stuff. Okay? Where do I get the 4 from? Right there. Where do I get the pi from? Right there. Where do I get the 10 from? What's the original problem 2 pages back? Okay, so let's go back. 2 pages back, consider a sphere. That's the starting radius. Okay, so you need to put that in there for r. Now, where does this come from? Because this is a change in the radius over time. And then you just solve for your dv, because the question was asking you how does the volume change. And I'll let you get the answer down, and let me explain a little bit about units here. Okay. Volume is a measurement of how much a thing contains. Volume could be in liters. Volume could be in gallons. But because the radius is in centimeters, we're going to say this volume is cubic centimeters. Now, do your units work out? They should, because you got centimeters and you got a square. That's square centimeters. When you multiply it by another centimeters, you have 3 total centimeters. Centimeter, 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 cubic centimeters. So this is a measurement of volume. It's a cubic centimeter. 1 centimeter. That's a measure of volume. Cubic, think of the cube of air in this case. Could be water, could be liquid metal, whatever. And that's it. So let me ask a question. Carly, what does dV dt stand for?
Change in volume over time.
Change in volume. So the volume is changing at 40 pi cubic centimeters per second at this one instant. What instant? When the rate of change of the volume is changing by 0.1 centimeter per second. Okay, so, okay, let's do a couple more. By the way, this is an exact answer, unlike a differential, which is an approximate answer, because of this word instantaneous. It's happening at that instant.
Are we going to do average too?
Yes, we're going to tie all that back in together later. Okay, new problem. Cylinder. Okay, like a water tank, or do you guys know what that might be? I don't know what that might be.
Oh, it's like a propane.
Propane tank. Okay, except,
That doesn't work here with gas.
yeah, I think it's better if water is draining, so let's just call this a water tank. Here's the problem. Water is draining from a cylindrical tank at 3 liters per second. How fast is the surface dropping? So I'm going to be referring to your sheet here. Your related rate steps are on here. Step number 1, diagram. Draw a diagram with labels in the given problem. They often don't have a picture. So I read the problem, I say, ooh, cylinder. So I draw myself a cylinder. Okay, so just kind of visualize what's happening. Okay, so draw a diagram with labels from the given problem. I don't know if I have any labels yet, so hold on. Goal, find what? What are we trying to find? The green underline, how fast the surface of the water is dropping. Water is here. Water's coming out this little spigot here. Water is then here. Water is then here. Water was here, then it's here, then it's here. Notice how this level is changing. What part of the cylinder do we call this? Height. That's the height of a cylinder. Now, I know the cylinder's height is this big, but the water is the volume part, and the height of that water is changing. So when it says, what are you trying to find? D what on the sheet? You're trying to find dH, dt. It doesn't say on this one, how fast is the height of the cylinder changing? That is the tricky part sometimes, is reading it and understanding what you're looking for. So in this case, you have to write dH dt, and I'm going to want you to always write the same thing as I don't know. That's what I'm finding. The last one was change in volume, dV dt. The other thing you want to do is data. Which quantities are changing, which quantities are constant. That's very important. Okay? So now, and I'm going to also put down which rates are given, are they positive and negative, and so on and so forth. This is the only number given to me. What does that represent?
The rate.
Rate of what? D something. Liters. You have to know something about liters. What's a liter measurement? Volume. So that's a dV dt. Your units are going to be very essential here. That's a dV dt. dV dt equals 3. Okay. Now, also on this piece of paper, it says in the middle of the data what quantities are changing and which quantities are constant. That's very important. If something's changing, you can't put it in right away. You have to take the derivative, then put it in. If something's not changing, you can put it in right away. We're talking about V, volume of a cylinder. You have to know volume of a cylinder, or you have to be given it. I'm going to rarely give this to you. You're going to work on these right now, except for the really key ones. Where's a volume for a cylinder? Volume equals pi r squared h. So I'm going to write that. V equals pi r squared h. Now, I didn't take a derivative yet. That's just volume. To get derivative, I would have to take the derivative of volume to get dV. So I'm about to take the derivative. However, radius and height. Somebody want to tell me about which one of those is changing and which one isn't?
Height's changing, radius.
Height's changing. Radius is not. You can see that, right? As it goes down, the radius stays the same. Okay, so this one is a very important one. That doesn't change. This does change. And since my problem says find dH dt, I want to leave that h in there. Because when I take the derivative of h, I get a dH dt. So how does this work now? Let's check it out. This you won't really have to do. Okay? They expect you to know in this problem that there's 1,000 cubic centimeters in a liter. Okay? So because this is 3 liters per second, you have to convert that to centimeters. Liters, and this thing is a measurement of height. You can't say I'm 4 liters tall. That doesn't make any sense. So you have to use centimeters, or if you have a conversion in inches, that's fine. Or if you have a conversion in feet or miles, that's fine too. They won't have you convert. This one's a little bit more challenging in that respect, so I'll just tell you.
It's going down.
And it's negative because it's going down, right? I thought that was going to come in later, but it comes in now, so I'm going to add that. That's a very forgotten thing too. This is negative because of its dropping. Now I don't want this to be in liters per second because liters is not a measurement of height. So I have to get it into centimeters, and that's how I convert it. So instead of doing negative 3 liters per second, I'm going to do negative 3,000 cubic centimeters per second. Okay, so where do we go from here? Question is find dHdt. I did all this already. Then you start with your volume formula, then you take your derivative. Go ahead and take your derivative. Now let me ask you a question before you get too far. Do you need a product rule here?
Yes.
You almost always need a product rule just by looking at that, but in this case you don't. Why not? Because R doesn't change. R is a number. I don't know what it is yet, but because R doesn't change, it could be 5, it could be 2, it could be 18. So it's a number. You don't have to take a derivative of it because it's a number. So this is like pi times 3 squared times h. So how do I take the derivative of that? That's what you get. Don't forget your dHdt. Derivative of h is 1, dHdt, the r squared stays there. Then what? Your dVdt's number you put in for dVdt. You know pi is 3.14. You don't know r, and you don't know dHdt because that's a question mark. So you leave it and solve. Now what on earth does that answer mean? This is what the answer means. The height changes at 3,000 cubic centimeters per second divided by pi times whatever the radius is. Now I didn't tell you the radius, so you can't really go farther on this problem unless you knew it. They often will tell you the radius. The radius of a tank is 4 centimeters. So this works for any tank. If it's a 4, you put a 4 in there. If it's a 10, you put a 10 in there for R. It doesn't matter. This is just a formula. Maddie, question. This is a formula for what? What's its answer represent? The change in height of the cylinder. Good. Willie, what would the units on this answer be? Change in height. Centimeters. Centimeters? Close. dHdt. Centimeters per second. Does that make sense? Let's do a unit analysis. The numerator is cubic centimeters per second. The denominator, pi doesn't have units on it, is r. What would a radius measurement be? Centimeters, but it's r squared, so it's centimeters squared. So this is over 1. You can't divide fractions. You can only multiply by the reciprocal. So you get centimeters cubed per second times the reciprocal, which is 1 over centimeters squared. 2 of these cancel with 2 of those, so you're left with centimeters per second. Your units make sense. Okay? Steps for related rates problem. These are my old steps. I got these new ones off the internet, so I decided to go with the ones I put on here. So I'm not going to go through these. Here's another problem. Classic problem. Hot air balloon problem. I'll tell you what's happening in a second. Let me give you just a chance to write it down. All right. This question is not great, so I'll tell you what the question would look like on the AP exam. Here's what the question looks like on the AP exam. You are standing 500 feet away from the bottom of a hot air balloon. The hot air balloon is rising straight up vertically. There's no wind, so it's not being blown left or right. It's just going straight off the earth. How fast is the balloon rising? Okay? So you draw your picture, and I would start with, here's you on the ground. Yay. Here's the balloon in the air. Yay. You are 500 feet from the balloon. Okay, that'll be given to you. And then the balloon is going up. Here's little arrows. Now, you have to identify that often on these problems you're going to have a triangle. Triangles are going to be the key. What kind of things, formulas do you use with triangles? Pythagorean theorem. What else? SOHCAHTOA. Anything else? Similar triangles is on the list. And maybe that works when you do the lamppost problem later, that's similar triangles. Anything else? 1/2 base times height if we're talking area. Anything else? Hear this formula? Yeah, okay, we're not going to use that one. Okay, that's a good one too, but I don't even remember that one. So there are lots of triangular formulas. Sometimes it doesn't matter, but I would say 50% of them are Pythagorean theorem. Looking at this and looking at what you're given, do you think you're going to use Pythagorean theorem? I think we're going to use SOHCAHTOA too because of the theta and the angle. Now, that says pi over 4. Pi over 4 often confuses people. How many degrees is that? 45. So sometimes they might say degrees, but usually with the calculus problems, they'll always be in radians. Not usually. Anything on the AP exam will always be in radians. So they're not going to say you're looking up at it as a 45-degree angle. They'll say your angle of inclination is pi over 4 radians or whatever. And now you have this given to you also. Okay? d theta dt. Dominic, what does d theta dt represent? What would that mean in this problem? The change in theta over time. What would theta stand for? Change in theta. Let's use a different word besides theta. What does theta mean?
Pi over 4.
It is pi over 4, but that's one instant. What does theta mean in a problem? Does it mean length? No, it doesn't mean length. What does it mean in this kind of problem? The angle. It's the angle. So watch me watch my balloon ride. So you ready? I'm looking at the balloon go up in the air. The angle is changing. So the instant we're talking about right here at this snapshot is when the balloon is 45 degrees with the horizontal. It's not way up there at 80 degrees. It's not just off the ground at 12 degrees. It's kind of like halfway between straight above me and right there 45 degrees. So that's your snapshot. Theta is one instance of this angle. This is a rate of change that they give you. They probably won't say d theta dt, but I'm starting early. They'd probably say the rate of change of the angle is 0.14 radians per minute. So how do you do this one then? How fast is the balloon rising? We need a d something dt equals question mark. D what dt? In my case, the way I labeled it is height. Sometimes people like to use the good old Pythagorean theorem things, and they like to do A, B, and C, which is fine. Then you're going to call it dA dt. It doesn't matter. But because I labeled it as height of the balloon, and probably because this is how fast is the balloon rising, I guess the height would be, how fast it's going up, how high, the rate of the change of the balloon. It's speed. We're calculating its speed. Okay? So what do I do? So find the HET, I did that with my question mark. We started with deciding that this was trigonometry other than Pythagorean theorem. So I decided to use tangent. Why not sine and cosine?
Because you have the opposite and the adjacent.
Yeah. This question might ask you this. How fast is the balloon moving away from you?
Oh, yeah.
That would be the hypotenuse change. So what do you want to call hypotenuse? That would be C, I guess. I don't know. It doesn't matter. Then I would say you're looking for dc dt. But it's not asking you how much this is changing. It's asking you how fast it's rising. So you have to know which one that is. You have to have some knowledge of the world around you. So that's a height, a dHET or dA. So I chose to use tangent. 500, normally it's tangent is TOA, T-O-A, and tangent is opposite, H over adjacent, right? TOA, adjacent. Bria, I decided to put that 500 in there and not put the letter A. Why? And it's not going to change. You have to determine what's changing and what's not changing. That's one of the steps. The 500 is not changing because the wind is not moving the balloon left and right. It's only going straight up. If it was moving left and right, I would then have a changing X direction. I'd have a changing Y or H direction. I'd have a changing C direction. It gets more complicated. You can do this. It's not that bad. When something's not changing, throw it in right away. Tank problem. If I did this problem again and I told you the radius was 3, immediately I would have put 3 in there. Do that before the derivative, because then you don't have to know, am I doing product rule or not product rule? So this one will be easier for you because they'll actually give you a number for that radius. This one, the 500 doesn't change, put it in right away. Go ahead and take the derivative, everybody. Oh, you gotta remember something now. And I have to quicken this one up a little bit, you guys, because time's almost up here. It's taking a little longer than I thought. Secant squared, derivative tangent, right?
Yeah.
Did you remember d theta dt? Okay, that's part of the implicit differentiation chain rule. This is not tangent t. It's tangent theta, so you need a d theta dt. And then this is simple. A lot of people like to use quotient rule. I hope you didn't. I hope you said 1/500h. And then the derivative of 1/500h is 1/500. And then don't forget dh dt. Yes, David?
Why don't you just multiply over the 500 and then find dh that way so not take a long.
Feel free. Go for it. Doesn't matter. Because looking at this, you multiply both sides by 500 is 500. Don't forget your d theta dt. So then let's start plugging in. Do I know theta? Yes, pi over 4. Do you know secant pi over 4? I don't know. Maybe you do. I hope you do. Do you know d theta dt? Yes, put it in. Do you know dh dt? No. So you put everything in. And you solve for dh dt. So you could have multiplied by 500. That's actually a good idea, David. And then all you have to do is just figure out whatever this is times 500. Okay. So that's about it. I had a truck problem, which is kind of cool too, but I'm not going to get to it. Okay, and do I have the answer on the next page?
No, 2 squared 2 over 2.
Secant of pi over 4 is the square root of 2. Okay, so hopefully you knew that.
So it's just 2?
So it's just 2. Square root of 2 squared is 2. So 2 times 0.14 times 500. 140. Don't forget your units. This is in feet. Okay, so I think it said per minute on the last slide. So per minute. So it's feet per minute. Okay? Now, homework. You get 2 worksheets today because it's bonus day. The first worksheet I'm giving you right now is your optimization review. There are 3 of them on here. I would love you to do all 3. If you could only do 2, that's fine. The last one's a little bit more challenging. The good news about optimization review is that I gave you the formulas. You don't have to come up with them on this page. I will do a couple more tomorrow where I don't give you the formula. Next page. I'll be right there. 3 related rates questions. So you've got 3 optimizations and 3 related rates. You will struggle with related rates because it's early. There's nothing wrong with that. You will not be quizzed on related rates till mid next week. Oh, I did? What's that?
Can you say it for us?
These problems on the first one were created by calculus students. At the end of the year, after the APCalc exam, I had them write their own questions. Who got the short one? James? You need a related rates one? What did we give up with that one? Yeah, I don't remember. I know that the magic carpet ride was with that Egyptian I had in class. Oh, name escapes me.
I can't even name that. I know exactly what you're talking about.
Picture him.
It's just seeing. They look excited about this delayed rate, so.
It's interesting stuff. Although it's challenging to get started.
Didn't see that.
No, it's not.
No, don't care.
It's not.
You gotta remember the.
So then if I multiply
Oh, hey, Brian.
by
APCalcRR.
I would get h equals tan theta times 500. So what I have dh over dt equals negative secant squared theta times 500.
Times d theta dt. It's the same thing right here, except you Don't say negative, it's not negative.
Oh, it's not, okay, yeah. Alright.
Homework for the class.